Hello everyone. The topics of this video are signals operations, digital resampling, and discrete time signal classifications. In previous video, we covered these two topics, continuous to discrete signal and discrete time signal models. And the next video, we will cover these two topics, and that will end this chapter, which is discrete time and system. Okay, so let's start with signal operations. In signal operations, we will cover these important operations. The first one is time shifting, basically delaying the signal or advancing the signal. Time reversal, when we rotate the signal around the vertical axis. Time compression, when we reduce the samples. And time expansion, when we expand the signal. Okay, the first operation we will talk about time shifting. So basically, if I have a signal x of n and I created a new signal y of n, which is x of n minus, let's say, 5. The new signal will be exactly the same shape as the previous signal, but shifted to the right 5 units of samples, delayed. If you think of it, let's say this is the signal x of n, and this is 1 and 2. Now I am creating the signal y of n, which is x of n minus 3. So if I want to know what is y of n at n equal, let's say, 4. So then I plug here for n4, 4 minus 3, that is 1. So the signal x of n at n1, which is these samples here, will be mapped at n4, which is here. And the same thing, if I want to know what is the signal at n5, I plug here n5, 5 minus 3, that is 2. So that's the value of the signal at location 2 will be mapped at 5. So this is the signal here, or the sample. So it will be mapped at 5. And the 0 will be mapped here. So this operation, basically, x of n minus 3 shifted this signal 3 units to the right. So this is shifted here, and this shifted here and here. Now, mathematically, you can think of it as follows. If this is the signal, and it exists in this range, so if I plot it, it will be this one. It exists from n3 to 10. Now, if I create a new signal, y of n, which is x of n minus 5. So that's basically, I am shifting this signal x of n 5 units to the right. So that's 3 plus 5, that's 8. So that will be here. 10 plus 5, that's 15. So that will be here. Let's clean up. Also, I can think of it mathematically as follow. Now, if I want to create this new signal, which is x of n minus 5, basically wherever I see n here, I replace it by n minus 5. So that will be, and now here, I need this to be n by itself. So I'm going to add 5 to every side of the equal signs or larger. So that would be 5 plus 3, that's 8. Here it will be n. 5 plus 10, that's 15. Now if I plot this signal in this range, it will be this. So it exists from 8 to 15. Now if I want to create a new signal that looks like this, now these basically mean shifted to the left by 10 units, or it means it's advanced 10 units of time. So this is basically y at n equal 10. It's the same as x, 10 plus 10, that's 20. So if x of n is this one, and there is a sample here at 20, it will map at y of n at 10. So this sample will be now here. So that's advancing the signal by 10 units, or shifting to the left by 10 units. So that means this signal here, I shifted 10 units to the left. So the 3 will be 3 minus 10, that's minus 7 here. 10 minus 10, that's 0. So that's here. The shape of the signal doesn't change. And if I want to find x of n plus 10 mathematically, it will be 0.9 and replace n here by n plus 10, and here replace n by n plus 10. Now I will subtract 10 from here to have n. So 3 minus 10, that's minus 7. 10 minus 10, that's 0. And that's this plot. All right, just remember, minus mean delay or shifting to the right, plus mean advancing the signal or shifting to the left. Now, practically, I can delay the signal. So if I have a system here and there is an input, the output here could be a delayed version of the input, maybe by 3 units, 3 seconds, 3 hours. But advancing that, practically, we cannot build a system that will advance the signal. Basically, I cannot have a signal x of n that started at 12 noon and the output signal will be 3 units earlier. That means 9 a.m. So how can the system predict the input and give you 3 hours earlier what will be the input? So advancing or shifting to the left is mathematical operation that help us process signals, but it cannot be built as a system. Okay, the next is time reversal. So basically, if I have x of n, this signal here, and I created y of n, which is x of minus n. All you do is you rotate the signal around the vertical axis. So that will be the signal here. So the 3 will come to the minus 3, and the 10, when you rotate it, it will come to the minus 10. And mathematically, let's define x of n as, now if I want to find y of n, which is x of minus n, wherever I see n, I replace it by minus n. So that will be, now this is, if I want this to be n, I will multiply by minus 1. And remember, when you multiply by minus 1, you change the direction of the sign larger or smaller. So if I multiply everything here by minus 1, then this will be minus 3. Now this direction will change, and this will be n, and this direction now will change. And I can rewrite this. This basically, n is larger than minus 10, so I can write it this way. And here, minus 3 is larger than n, or n is less than minus 3. Can write it this way. And if you plot this signal will be this one here, and it exists from minus 10 to minus 3, from minus 10 to minus 3 here. Now we may have operation that involve shifting and time reversal. Let's clean up first. So I have the signal x of n. And now I need to create this signal. There are different ways of doing this. To get to this signal, I can first find x of minus n. It will be the same as this one. And then to get the 20 here, I can do the following. X of minus n minus 20. See, when you have minus time minus, you get plus 20, which is this. Minus time n, you get minus n. So this signal is exactly this signal, what we are after. So how do we get this? Well, this is coming from here by shifting to the right 20 units because of the minus sign here. So I shift this signal here to the right 20 units because I have the minus here. And if I do this, 20 plus minus 3, that's 17. 20 minus 10, that's 10. And this is the signal. Or if I want to just carry it out mathematically and use some software to plot it, I can say this is x of 20 minus n. Wherever I see n, I replace it by 20 minus n. So that will be 0.9, 20 minus n. And n is between 3 and 10. And I want to get rid of the 20. So I will subtract minus 20 from both sides. So this will be 3 minus 20 minus 17 minus n, 10 minus 20, that's minus 10. And I need this to be n, so I'm going to multiply each side by minus 1, so that will be n, and the sign will change, and this will be 17, and this will be 10. And this basically n is larger than 10, so I can write it this way. And this basically n is less than 17, so that's this way. So I plot this signal in this range from 10 to 17, which is this. Okay, the next one is, let's clean up, compression or downsampling and decimation. There is a difference between downsampling and decimation. Downsampling is pure, just reduce the number of samples. Decimation involves filtering before downsampling. And we express the downsampling with this down arrow. So this is the new signal, which is the same as the original signal, but downsampled by a factor m. So if m is 2, that means I downsample the signal by a factor of 2. I reduce the size of the signal by a factor of 2. So how we do this downsampling without decimation? If I do the downsampling by a factor of 2, basically I keep one sample and I ignore the adjacent one. Then I keep this sample and I ignore this, and so forth. So this 0 will be here. This will be this one. Then I ignore this one. Then this one will be this. Then I ignore this, and this will be this one. Downsampling by a factor of 3. Now I will keep one sample and ignore 3 minus 1 is 2, and ignore 2 samples. So this will be this way. Here m is 3, and ignore these 2. Then keep these, ignore these 2, then keep these, ignore these 2, and keep these. So it will be this way. The 0 will be here. The next sample will be this one, and the next sample will be this one, and so forth. So I reduce the size of the signal by a factor of 3. Later on, we will see decimation. Decimation means you filter out before you downsample, because when you downsample, aliasing may happen. If I have this signal, for example, that it was a continuous signal and the bandwidth was 20,000 hertz and the sampling rate was 40,000 samples per second. Now, if I desample this discrete signal further down by a factor of 2, it's like I took a sampling of this rate, 20,000. Now, aliasing will happen. The bandwidth here is 20,000 and I'm sampling not twice it, exactly the same. So to avoid aliasing, we do first decimation, which means I eliminate all frequency above 10,000 first. So now this signal, the bandwidth will be from 0 to 10,000 hertz. Now if I downsample it to 20, I will avoid aliasing because 20 is twice the highest frequency in the bandwidth. Later, when we do digital resampling, we will talk more about it. Let's clean up. Now, we can think of this mathematically as follows. If I think of m here, let's say 3, downsampling by a factor of 3. If I want to know the sample of this new signal at n0, it will be the sample at the old signal, 0 times 3, that's 0. So same samples. Now, if I want to know what is the new signal at n equal 1, 1 here times 3, that's 3. So it's the third sample of the old signal. And if I want to find the second sample in the new signal, it will be 2 times 3 is 6 of the old signal. So the second sample in the new signal is the same as the sixth sample in the old signal. So if you notice from here to here, I am missing x1 and x2. So I kept one sample and I ignored 2 samples, which is m minus 1, 3 minus 1 is 2. So that's the 2 samples I ignored. From here to here, I'm missing x4 and x5. So I kept x3 and I ignored the next 2 samples. So I got to x6. Okay, so the next one is upsampling and interpolation. Upsamplings, I increase the size of the signal by inserting zeros between the original samples. Now with interpolation, then I use some interpolation method to estimate the value of the zeros using the adjacent samples, so the signal will be smooth. And mathematically, we express upsampling with this upward arrow, and it's the old signal n divided by L. So if I upsample by a factor L equal 5, that means I will insert zeros between samples equal L minus 1. So that means 4 zeros I will be inserting between samples. In this example here, from here to here, I upsample x of n by a factor L equal 2. So that means L minus 1 is 2 minus 1 is 1. So I insert 1 0 between samples. And that is the new signal with L equal 2. Now interpolation means the following. These zeros here, I will interpolate their values by using the adjacent samples. A simple interpolation could be linear interpolation. So the value of these 0 will be the average of these and these. So the upsample signal, instead of up arrow, now we put this I, means interpolated. For example, if I want to estimate this 0 here, so I want to find out what this value should be. So the interpolated at n equal 3 will be the value of that sample in the upsample signal, which is in this case just 0, plus the value of the upsampled 1 unit earlier and 1 unit after divided by 2. That means I take this one here, which is this, and I add to it this value, which is this value. Then I divide by 2. So I'm averaging these two values here. And that will give me this value. And the way to interpret this equation is basically the following. If this argument is not an integer for any value of n, then you insert a 0. So for example, let's say L equal 5. So n over L, which is n over 5, this will be only integer for the following values of n: 0, 5, 10, 15, and so forth. When x n over L, this is not an integer, for example, n is 7. So that will be x 7 over 5. That's not an integer. So you put a 0, this one. Let's take this example. So we have here a signal which is pure sinusoidal. So its digital frequency f will be 1 over 4. So 1 cycle per 4 samples. And if you think of it, the sign, if it's an analog, it will be like this one. So there are 4 samples per cycle, 1, 2, 3, 4. Okay, we have this discrete signal, that's the plot, and we want to expand it by a factor of L equal 2. And then we want to also interpolate the expanded signal using just simple linear interpolation. Okay, so to expand this by a factor of 2 without interpolation, L minus 1, that's 2, minus 1, that's 1. So I will add 1 0 between samples. So this will be this one here, then I add a 0, then this will be here, then I add a 0, then this will be here, then I add a 0, and this will be here, and so forth. Now interpolation using this equation is the following. For example, I want to interpolate this 0 here. So xi1 equal 0.5 x upsampled 1 minus 1, that's 0. So that's this one, plus the upsampled 1 plus this one will be 0.5. 1 plus 1 is 2. Now this value here is this, which is 0, plus This is the upsampled at 1, which is this one, 0, plus this one here, the upsampled at n equal 2. This is n equal 2, and the value is 1. So this just 0.5, which is this 0.5, and so forth. Now this upsampled signal looks like more a sine wave versus this one that doesn't looks like a sine wave. And the frequency of this new signal is reduced by a factor of 2, or the fundamental period increased by a factor of 2. Here, let's see. F is, let's see how many samples. 1, 2, 3, 4, 5, 6, 7, 8. 1 cycle per 8 samples. Versus this one, the frequency was 1/4, 1 cycle per 4 sample. The fundamental period here, N0, was 4 samples. The fundamental period here, N0, 8 samples. So upsampling increased the fundamental period by a factor of 2 for L2. Reduce the frequency by a factor of 2. Okay, let's now look at the digital resampling. When we do a digital resampling, sometimes you have old equipment and new equipment. The old equipment probably work at a lower sampling rate, maybe 4,000 samples per second. Now the new equipment work at a higher sampling rate, maybe twice. So how will these two systems communicate with each other? So now you have to do digital resampling. So these, maybe that is 4,000 per second, this is 8,000 per second. Now you have to upsample the output of this signal by a factor of 2 so this can analyze the signal and communicate properly. Or it could be the opposite, you downsample it. And sometimes you upsample it not by an integer, like in this case you upsample it by L equal 2. Sometimes you need to sample it by a fraction, 2.5. So how will we do that? So let's look here. First, without the summation, here I downsample by a factor of n. Now in practice, if you downsample, you have to eliminate high frequency from the digital signal. So when you do downsampling, aliasing will not happen. So in this case, we do first anti-aliasing filtering. So if I have a digital signal like this one, for example, and originally it was sampled at 8,000 samples per second. Now I want to downsample it to 3,000 samples per second. Now when you downsample to 3,000, you are assuming the highest frequency or the bandwidth should not be larger than half the sampling rate. So that is the bandwidth. While here, when they sample it at 8,000, the bandwidth is 4,000. So to downsample to the 3,000, that means you have to get rid of all frequency above 1,500 from the original digital signal. So I take it to anti-aliasing filter with a filter cutoff frequency 1,500. So I take this through this low-pass filter with this cutoff frequency to take all frequency above the 1,500. Then the output of this filter, I will do the downsampling now, and I will be avoiding aliasing. So now I can reduce the number of samples from 8,000 samples per second to 3,000 samples per second. I lost some high frequency because of the filtering here, but at least I avoid this high frequency to be aliased or act like low frequency and distort the signal further. Now, upsampling with interpolation is the following. This is upsampling, no interpolation. Now, with interpolation, I upsample the signal by a factor of L, so I increase the size. Then I use interpolator filter. That filter could be as simple as linear interpolation. If I want to estimate this value, I take the average of the two adjacent signal. Or it could be a more sophisticated like the sync interpolation. If I want to estimate this value, then I use this sync interpolation. It's more complex, but give you a better accuracy. Why? Because now with this sync interpolation, you are not just using the two adjacent samples, you are using even further samples. So you can see the behavior of the signal by using 5, 7, 8 samples to estimate one sample. Now, what if we want to upsample the signal not by a factor of 2, 4, 8, but by a fraction, something like this? I have a signal with 100 samples. Now I want to increase it to 450. So that means L is 4.5. Basically the new sampling rate divided by the old. So now that's 4.5. So I want to upsample it by 4.5. So how do we do this one? Now with this case, we have to use a combination of upsampling and downsampling. So I can do first the upsampling by a factor of 9. So now the signal here will be 9 times 100 is 900 samples. Then downsample it by a factor of 2. So now the signal here will be 450. And that's how we accomplish upsampling by a fraction. The other way, I can do first the downsampling by a factor of 2. So the 100 now will be 50 samples. Then here I upsample it by 9 to get the 450. 9 times 50, that's 450. Now, which one is better? Do I do upsampling then downsampling, or do I do first downsampling then upsampling? In general, it's always better to do the upsampling first than downsampling, because when you do the upsampling first, you still have these original samples of the signal. So you can use them to interpolate these, then do the downsampling. Versus this method, when you do downsampling, that means I am already getting rid of some of the original samples in the signal. Then I do the upsampling. Now when I do interpolation for the upsampling, I don't have many of the samples of the signal to use to interpolate the zeros. So it is always better to do upsampling first than downsampling. Now, if L over M is coprime, then it will not make a difference to do first upsampling than downsampling or downsampling than upsampling. Like, for example, 2 and 9. This is coprime. 2, you cannot find an integer that is divisible by 2 and by 9 other than 1. But 4 and 6 will make a difference. If you upsample by 4, then downsample by 6, then do this one first. Because 4 is divisible by 2 and 6 is divisible by 2. Let's take this example. This example shows the impact of upsampling first or downsampling. So we have this signal x of n, which is cosine pi n, and this is the plot of it. Now, part A, we want to do first upsampling by a factor of 4, followed by downsampling by a factor of 2. So if I upsample it by a factor of 4, that's when between samples I put 3 zeros. 4 minus 1 is 3. So between adjacent samples, I put 3 zeros. That's 1, 2, 3. Then downsample by a factor of 2, m equal 2. So that means m minus 2 is 1. So I keep one sample and delete adjacent, then keep one, then delete the adjacent. So I will keep this one, delete this, keep this one, delete this, keep this one. So this is the signal by upsampling by a factor of 4 and then downsampling by a factor of 2. So L over M is 4 over 2. These are not coprime. So now let's see the other way around. Do first the downsampling, then the upsampling. So part B, I will do the downsampling by a factor of 2, then upsampling by a factor of 4. So downsampling by a factor of 2, I keep 1, I delete this, I keep this, I delete this, and this will be the signal. Now, I upsample by a factor of 4, I put 3 zeros between adjacent samples. So this one will be this, then I put 3 0, then this one will be this, then I put 3 zeros, then this one will be this. Now these two are different. Upsampling first, then downsampling, at least it keeps this shape of the wave up and down. But when we downsample first, then upsample, now the signal looks totally different. We lost these negative samples here. Why? Because when we did downsamplings, we never included these in the signal here. Then when we do interpolation of this one, I will be using all these positives. So because 4 and 2 are not co-prime, it's very important to do upsampling first, then downsampling. Let's clean up. In part C, upsample by a factor of 3 and downsample by a factor of 2. So L over M is 3 over 2. These are co-prime. So really it will not make a difference if I do upsampling first then downsampling, or if I do downsampling first then upsampling. Will not make a difference. And we can see here, this is the original signal. So if I do the upsampling first by a factor of 3, 3 minus 1, which is L minus 1 is 2. So I put 2 zeros between adjacent samples. So this will be this one, then I put 2 zeros, then this will be this one, 2 zeros, then this will be this one. Then I do downsampling by a factor of 2. So I keep these, I delete these, I keep these, I delete these, I keep these, I delete these, I keep these. And that will be the signal. Upsampling by a factor of 3, downsample by a factor of 2. Let's do D, the opposite. So I will do downsampling by a factor of 2, then upsample by a factor of 3. So downsample by a factor of 2, I keep these, I delete these, I keep this one, I delete this, and I keep this one. Now upsample by a factor of 3, this sample will be here, then I put 2 zeros. This sample will be here, 2 zeros, this sample will be here. If I compare these two, they are the same. Why? Because L over M is a co-prime. So it won't make difference you do downsampling or upsampling first. So in general, if L and M are co-prime, which is to say they have no common factor other than 1, then the operation of expansion and compression are commute. In praxis, ordering may change aliasing and speed of operation. In general, it's always better to do upsampling than downsampling. Even though upsampling than downsampling, because you are increasing the number of samples, the operation, the processing, the memory will be more. Then you do the downsampling. Versus when you do downsamplings, you're already reducing the data. So you're going to be using less memory. So you're going to be using less processing. But then aliasing may happen. Okay, the next one is discrete time signal classification. So we're going to define causal, non-causal signal, even and odd signals, periodic and aperiodic, energy and power signal. So the first one is causal. That means the signal x of n only exists for positive n. So it starts 0 and keep going. For n negative value, x of n is always 0. It doesn't exist. Then we say the signal is causal. Non-causal signal is a signal that exists for positive and negative n. So it may have value here and also for negative n, negative 1, negative 2, it has some values. Then we say non-causal signal. Anti-causal signal, that means the signal only exists for negative n values. So it is always 0 here, but it may have values for negative n and so forth. Now, even and odd signal. A signal is even if this condition is met. That means the value of the signal for n1 is the same as the value for the signal at n minus 1, or n2 same as minus 2. So if you plot it, it will look like this. So basically around the vertical axis, it's like a mirror image. This is n1, same value here for minus 1. n2 is 0, n minus 2 is 0, and so forth. Then we say even function. A cosine function is an even function. Odd function has to meet this condition. So the value of the signal x at n1 is the same as magnitude, as n minus 1, but inverted. So if x of 2 is 10, then x of minus 2 will be minus 10. Then we say the signal is odd signal. And if you plot a sine wave, it looks like this. This is an odd signal. for n1 and this -1, they have the same magnitude. But if that was like, let's say 0.8, this will be -0.8 and so forth. Now, sometimes when the signal is even, odd, it can simplify the process. So if I have a signal that is not even, not odd, a signal like this, for example, that signal is not even, is not odd, but I want to make this signal as a linear sum of odd and even signal so it can simplify my processing. Then I can use this equation. If I add x of n with inverted version around the vertical axis and divide by 2, I will get even function. If I take the original signal and subtract from it the inverted signal and divide by 2, basically average it, I will get an odd signal. Now, if I add this even signal and odd signal, I will get exactly the original signal. And you can see it mathematically as follows. X of n divided by 2 plus x of n divided by 2, you get x of n, which is this. Now, x of minus n divided by 2, and subtract from it the same thing. X of minus n divided by 2, you get 0. So this is exactly the same as x of n. And if you want to see it graphically, let's take a simpler signal, like something like this. If this is the original signal, now I can create this one as follows. And I add this with this and divide by 2 to get this one. So then I will get this. So if that was, let's say, 6, now this will be 3. So that's even function. And to get this one, let's create this minus x minus n. So this is x of minus n. Now I multiplied by minus, so that will be this. Let's clean up. Now if I add this with this one, basically I add the original signal with this one and divide by 2. So I will get this one. Now that's an odd function. And this again will be 3. So now if I add, and this one, basically I add this even function and odd function, this one here will cancel this, and these samples will add up with these samples to give me the original. If that is the 3, will add up with this 3, I get 6, which is this. Okay. The next one is periodic and aperiodic signal. Aperiodic is non-periodic signal. A signal that looks like this, that looks like a periodic signal. And if I want to find what is the fundamental period, I can just add these samples, the number of samples here. So I have 1, 2, 3, 4, 5, 6. Then it repeats itself again. And if I want to find what's the fundamental frequency, F0 is 1 over N0. So that is 1 cycle per 6 samples. So I have every 6 samples, I get another cycle and so forth. And if I want to find it radians per samples, then I say omega 0 is 2 pi F0. So that will be 2 pi 1 over 6. That is pi over 3. So that is radians per samples. Now, if I don't have the graph to find the fundamental period and I have an equation, how do I find the fundamental period? So in general, if this condition is met, then we say x of n is periodic and the fundamental period is n. So if I don't have the signal plotted and I want to find out what is the fundamental period of a sinusoidal, something like this, then this condition, this means cosine 2 pi has to equal cosine plus n0, where n0 supposedly the fundamental period. So that will be, now for this to equal this, it is a must 2 pi fn0 equal an integer multiple of 2 pi, because the signal repeats itself every 2 pi. So it has to be m, where m is an integer. It could be 1 or 2 or 3 or 0 or a million. So then I can say Fn0 equal M. And then the digital frequency equal Mn0. And when M and N0, these are integers. When they are co-prime, that means there is no common integer that's divisible by M and N0, then N0 in this case will be the fundamental period. And the frequency will be M is the number of cycles per number of samples. Let's take this example. I have a cosine with digital frequency F. For part A is this one, part B is this one, part C is this one. And we want to know if it's periodic or not. And if it's periodic, what's the fundamental period? Well, F for part A is 3 over 15. So I can simplify it further by dividing by 3. So that will be 1 over 5. Now, this is coprime, integer divided by an integer. And this is an integer, M is 1 and sample is 5. So this is 1 cycle per 5 sample. So this is a periodic signal and the fundamental period is 5 because there are 5 samples per cycle and these are the 5 samples. 1, 2, 3, 4, 5. And this one, it repeats itself as this one. Now for part B, F is 1 over 1.7 pi. You can multiply numerator and denominator by any integer. This will never be an integer divided by an integer because of that pi. So this is digitally aperiodic. I can just keep going and going. The samples here will never repeat itself. Let's take part C. F equal 1 over 5.5. Now I need to make this integer divided by integer. So I can multiply numerator and denominator by 10. So that would be 10 divided by 55. Then I can divide both sides by 5. So this would be 2 divided by 11. Now this is a periodic because the numerator is an integer, denominator is an integer. And I simplify them to the lowest level where they are co-prime. Now these N fundamental is 11. I have 2 cycles per 11 sample. So these sample 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then it repeats. See, this is equal this. And this equal this. The last topic in this video is energy and power signal. If the signal is not periodic and it eventually die out like something like this, then we call this energy signal. And if I want to know what's the strength of this signal, I calculate the energy of the signal, which is the summation, the square of the samples. So that will be x of n squared. If the signal is real, that's the definition. But if the signal may be complex, I take the magnitude and I square it. And that will be the energy signal. Now, if the signal is periodic or it just keep going for a while and it may have look something like this, periodicity, then to estimate its strength, first I have to decide how many samples do I take, where I can see a rhythm, the signal starts repeating itself. Then I square all these samples and I sum them up, and then I average them by divide by n0. And this is the definition. Let's look at these examples. I have this signal x of n, and I need to determine its strength. Well, this signal is not periodic, so it will be 0 square plus 1 square plus 2 square plus 3 square, 4 square, 5 square. And you will get 55. Now, this signal definitely is periodic. So first I have to define the fundamental period. Well, I can consider these samples are where it repeats itself. So I have here 1 sample, 2, 3, 4, 5, 6. So n0 is 6. So the power will be 1 over n0 summation n0 to 5. So that means 0 square plus 1 square plus 2 square, 3 square, 4 square, 5 square. And if you do this one, you will get this value. How about this signal? Well, this looks periodic and it repeats itself for these samples. It starts 0 all the way to 5, then go back to 0. It starts 0 all the way to 5, then go back to 0. So here the fundamental period is 1, 2, 3, 4, 5, 6, 7 samples. So the power will be 1 over 7, and the summation n0 to n equals 7 minus 1 is 6. So it will be 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is 55, divided by 7. And that will be the value. Okay, this ends today's lecture and video. Thank you for watching, and see you next video.